Bonjour. Donc, je suis Franco Saliola. Je suis le nouveau directeur du CRM. And I'm delighted to welcome everyone here today for the the CAP-CRM Prize Lecture. The CAP-CRM Prize was established in 1995, and it recognizes exceptional research in theoretical and mathematical physics conducted in Canada. It is awarded jointly by the Canadian Association of Physicists, which is a professional association representing over 1,600 physicists and students in Canada and abroad, and the Centre of Research in Mathematics, mathematiques, which is an internationally recognized research institute in the mathematical sciences, and that holds several thousands of visitors every year. In addition to supporting research, both these outreach activities that encourage students to pursue careers in mathematics and physics. This year's laureate is Alexander Maloney, James McGill Professor of Physics at McGill University. So he is on leave this year from McGill and is at the university at Syracuse University. Professor Maloney earned his PhD in physics from Harvard University in 2003, and then held research position at the Stanford Linear Accelerator Center, the Institute for Advanced Study at Princeton. He joined the McGill faculty in 2007. Professor Maloney is a nationally recognized research that explores foundational questions at the interface of particle physics, gravitation, and cosmology, with a special focus on quantum gravity's deepest puzzle, including the quantum description of black holes. His research brings together ideas from across physics and mathematics. Through numerous conceptual breakthroughs, he has developed powerful tools that can be applied in deep problems in quantum field theory, quantum dynamics, and statistical physics. His pioneering work at the intersection of quantum information theory and foundational physics has helped cement Montreal and Canada's position as a leading center for research in this area. So we have invited Professor Maloney to give a talk today to a wide mathematical audience. And so I'd like to invite you to please join me in congratulating and welcoming this year's 2025 CAP-CRM Prize winner, Professor Alex Maloney.
Thank you. Thank you. So thank you for the very kind introduction. Of course, I'm tremendously honored to receive this prize. It's a great honor, and I'm delighted to be here talking today. Maybe I'll begin my talk with a series of apologies. So my first apology is that I'm a physicist and not a mathematician. Which of course, for which I need to profoundly apologize. But in this talk, what I'm going to really try and do is talk about the physics, but in a way that advertises to a more mathematical audience some of the mathematical ideas that are underneath. And the second apology is that in the interest of trying to talk to a broad mathematical audience, I think some of the experts might be a little bored. I encourage you to do Sudoku or Wordle or whatever it is you do, or ask questions, whatever it is you do to keep yourselves entertained. But I will try and at least start by keeping things rather general, with apologies to those experts in the audience. And finally, I'll emphasize that I do want to, my goal is to try and communicate clearly. So at any point, feel free to stop, interrupt me, ask questions if there's anything that needs clarification, or I can elaborate on in a way that would be useful. Okay, good. So in the view of having a good Friday afternoon's entertainment, to keep you all awake, let me start with something absolutely preposterous, okay? So I'll start with a completely preposterous quotation by one of my favorite physicists, John Wheeler. You can read the quotation. I'll read it along with you. It's an outrageous bit of propaganda. It from bit symbolizes the idea that every item of the physical world has at bottom an immaterial source and explanation. That which we call reality arises in the last analysis from the posing of yes or no questions and the registering of responses. In short, all things physical are information theoretic in origin. Okay, so outrageous propaganda here. Like, let's be straightforward about that. But the amazing and truly outrageous thing about it is that it's true, at least in a certain sense, in a way that I'll try and make precise and convince you of. It's true in a very certain sense. In particular, it's true in the sense that in many circumstances that we can analyze precisely, what we call classical spacetime, macroscopic spacetime, arises as the entanglement, the quantum mechanical entanglement of more fundamental degrees of freedom. Okay, so that's a very specific interpretation of this quote. But I think it means that at least in a certain sense, you can think of space-time and many of the objects that we think of as living on space-time, like gravity, quantum field theory, et cetera, as information theoretic objects. But in order to try and make this idea precise, what I really want to focus on, and what's the specialty of my work, is relatively simple systems. Systems either in a low number of space-time dimensions, systems with an extraordinarily rich degree of symmetry that will allow us to make some sort of precise statements where we can try and do exact analyses that are impossible in more complicated settings. Okay, and as a way of advertising to the mathematical audience, lots of interesting mathematics arises when you do so. And here I've listed a few. Oh, that's interesting. I've listed a few areas of mathematics that arise along the way. Okay. So what is my plan for this Friday afternoon? Well, first, this is where all of the experts in the audience can do Sudoku or something. First, what I'll do is I'll give just a very brief primer on some aspects of quantum mechanics and field theory, recognizing that this is a broad audience, trying just to establish a basic language so that we all know what we're talking about. I'll then talk about the sort of example that has inspired most of my research, which is a relationship between quantum field theory or conformal field theory and quantum gravity. And I'll talk in hopefully a straightforward way about the relationship between conformal field theory and black hole physics, how we can use ideas from gravity to learn about conformal field theory and vice versa. And then finally, I'll talk about some sort of more modern aspects of the subject that have been the interest of my research over the past few years, having to do with ideas in quantum chaos, random matrix theory, things like that. And actually, there's some surprisingly sophisticated things you can say about conformal field theories and about this general subject using some pretty interesting mathematical tools. So let me just start with a very brief reminder of what quantum mechanics is. Quantum mechanics is very simple. It says that when we study a physical system, the states live in a Hilbert space. The simplest example that you could think of is a two-dimensional Hilbert space or a two-dimensional vector space. And depending on who you are, you might call that many different things. If you're studying quantum computing, you might call that the basis states of that vector space 0 and 1. These would be the states of a bit turned into a quantum mechanical bit once you think about the Hilbert space. If you're a physicist, you might call it the states of a spin 1/2 system. We would call the two states the spin pointing up and the spin pointing down. If you're a gambler, you might call it the states of a coin, whose two possible states are heads or tails. If you're a mathematician, you might call the Hilbert space the space of holomorphic sections of the square root of the canonical bundle over projective space. Okay, that's the same thing. If you're a condensed matter physicist, you might call it the states of a particle moving on a sphere in the lowest Landau level when you turn on a transverse magnetic field. These are all different names for the same thing. Okay. The observables in the theory are operators. They're Hermitian operators that act on this Hilbert space. So for example, here I'm using the language of a spin 1/2 system, and observables are things that you use to answer physical questions. And the physical question, is the spin pointing up, or is the state of my bit 0, corresponds to an operator. And it's this projection operator. It's the the projector onto a one-dimensional subspace of this Hilbert space. Okay. And then quantum mechanics gets interesting. It comes to life when you consider not just a simple system like a bit or a spin 1/2 particle, but more complicated systems. And here, the basic thing to remember is that when you combine two systems, which each have individual Hilbert spaces H1 and H2, the state of the joint system lives in a tensor product Hilbert space. Okay. So in the case of 2 spin 1/2 particles, it would be a 4-dimensional Hilbert space because 2 times 2 is equal to 4. And that's where life gets interesting, because that's where entanglement arises. So for example, you could consider a more complicated system, such as one where you have a red spin and a green spin. And then you could consider states such as the one, oh, I guess this thing does not absorb, it absorbs lasers very well. Okay, so you could consider a fancier state like this one, which is not just the tensor product of 2 vectors in the individual Hilbert space, but rather is a linear combination or a superposition of such states. So this is a state where you have both spins pointing up in a linear combination with the state where both spins are pointing down. And we say that such a state is entangled. And one of the reasons why that's interesting is that if, for example, you were to just study the red spin and not the green spin, and you were to look at the observable that asks, am I in this state psi? Okay, so that's the projection operator onto that state psi. And you were to ignore the green spin, which means you trace over that part of the Hilbert space, what you get is the linear combination of the observable that asks, is the spin up? And the observable that asks, is the spin down? Okay, so what does this mean? This means that you could start in this definite quantum state, but if you were to ignore the green spin and only talk about the red spin, then what you would find is that with 50% probability it's up, or with 50% probability it's down. And the relationship with information theory arises because this probability distribution, where you have a spin that's got a 50-50 chance of being either up or down, has an entropy. In the language of information theory, you would call it a Shannon entropy. In the language of quantum mechanics, you would call it a von Neumann entropy. And of course, it has 1 bit of information. So that's quantum mechanics. Life gets much more fun if you consider bigger systems, like not just 2 spins, but a very large number of spins here, which I've arranged in a grid. And then we could allow them to interact in some way. Okay? So in the limit where you have many, many spins, then this is not just a quantum mechanics system, but it's what we know as a field theory. A field theory is very simple. It just means that you have many observables, and that in fact you have an observable at each point in space. Okay, so previously I talked about an observable of a single spin, and there were only, there was just 1 observable that I was talking about that asked if the spin was up. Here, because you have a spin at each point in space, for example, you have observables at each point in space. Observables that ask questions like, which direction is the spin pointing here versus which direction is the spin pointing at some other point. Okay. So that's what a field theory is. And then the most interesting case, and in some sense the most important case, is when these field theories have additional symmetries. And one very simple such symmetry that could arise is a conformal symmetry. So why does that arise? Well, if you study a system of interacting spins like that, then there'll typically be some sort of length scale, which is the correlation length between the 2 spins. Okay, so typically spins will be correlated when they're nearby, and they'll be uncorrelated when they're far apart. So that means there's a typical length scale that describes the correlation, the distance with which 2 spins are going to be correlated. And then if you tune the model, so for example, if this is at finite temperature, you might go to a critical value of the temperature, or you might go to a critical value of the couplings between these spins. You can go to a point where that correlation length diverges. Okay. And what does that mean? Well, the correlation length defines a length scale in the theory. And if that length scale is going off to infinity, that means there's no length scale in the theory. So that means it's scale invariant. Okay. And to say that a little bit more mathematically, we refer to it as conformally invariant. And a field theory of this type is just a normal quantum mechanical system, just like what I described earlier, with, for example, a bunch of spins, but you've gone to a special point where it has no correlation length. So it has no length scale, and then it has this additional set of symmetries, and is known as a conformal field theory. Okay. And so what are conformal field theories? They're normal quantum mechanical systems, but they have more structure. So for example, they have a list of states, okay, just like in a usual quantum system. They have a list of observables. It turns out that because of the magic of conformal symmetry, the states are in one-to-one correspondence with the observables. And then there's a bunch of data that goes along with this list of states and observables. So first of all, each state has an energy, right? Something you can measure. In the language of conformal symmetry, sometimes you call that a scaling dimension, but you can also just think of it as an energy. And the other thing is that, remember, these observables are Hermitian operators acting on the Hilbert space of the system, so you can multiply them together. And so along with these conformal field theories, we have some sort of product rule that tells us how we can multiply observables together. And in the case of a conformal field theory, you can write all of this out explicitly. And there are a bunch of consistency constraints that this data that defines a conformal field theory obeys. So, for example, the spectrum of the theory, the list of energies, and the coupling constants of the theories, these coefficients that appear in what's known as the operator product expansion, because we're multiplying operators together. That data is subject to some consistency conditions. In the mathematical literature, this data subject to these consistency conditions is known as a modular tensor category. But in the physics literature, we call these consistency constraints just the constraints of unitarity that a conformal field theory must obey, the solution of which is a solution of the so-called conformal bootstrap program. Okay, so if you go to many physics departments nowadays, people are very excited about the conformal bootstrap program. It's sort of like the Manhattan Project of theoretical physics or the Genome Project of theoretical physics. It's this grand classification problem where you write down the data that defines a conformal field theory, and you try and solve all of the constraints. Okay. Yes.
Is this all about 2D conformal field theory?
So this structure so far is very general. Okay, there's an operator product expansion, there's a spectrum. In higher dimensions, I have to specify additional conserved quantities in addition to the energy. I have to specify some spins. But the general the use of the word modular tensor category is specific to 2 dimensions, which is mostly what I'll be talking about today. But of course, there are similar structures much more poorly understood in a higher number of dimensions. Okay. Good, great, awesome question. Good, any other questions? So solving these constraints, these consistency conditions that the data of a conformal field theory must satisfy is this grand, vast program in theoretical physics. If you solved it, you would be rich and famous. Well, you would be famous, okay? Except for a few relatively simple examples, it has not been solved in general. Okay. But in some cases, especially when you're considering relatively simple systems in a low number of space-time dimensions, you can solve it. Okay, and one case you can solve it is this case that I wrote down for you over here. You consider a bunch of interacting spins in this 2-dimensional grid. You go to a critical point. You can write down the consistency relations and you can solve it. Okay. And what does that mean? It means you have a list of observables, a list of energies, and a list of coupling constants. Okay. So in this case, what are the observables? Well, there's an observable I called the identity operator. Okay, it does nothing. There's an observable I called sigma. What does it do? It measures the value of the spin at a particular point. There's an observable I called energy, which measures the amount of energy at a particular point. Okay, and you get a list of numbers. Okay, that tells you the spectrum of the theory. And you can learn the coupling constant of the theory. This is what I referred to as the operator product expansion coefficient, this C up here. Okay, and in this case, there's only one non-trivial coupling constant, And it tells you that two spins, you multiply them together and you get an energy. So in the language of physics, it's roughly speaking related to the fact that the Hamiltonian is quadratic in the spin. Okay, if you've seen that, like a Gaussian. Good. Okay. But remarkably, and what I want to focus on today is that actually this entire structure can be used to understand and address some rather deep questions in quantum gravity. Okay. Now, what the hell is the relationship between conformal field theory and gravity? It seems a little random, so let me justify that a little bit. So, as you know, or have heard, classical gravity is Einstein's theory of general relativity. So it's a theory of dynamical spacetimes. And the states of this theory are spacetime geometries. Okay? But understanding this at the quantum mechanical level, so for example, understanding what the corresponding Hilbert space is and the observables are in the language that I used earlier, that is very much a mystery, except in one special case where I think it's fair to say the problem is solved, for some definition of the word solved. Okay? And the exception is gravity in what's known as anti-de Sitter spacetime. Okay? And here, what I don't mean is that we fix the spacetime to be anti-de Sitter space. Rather, what I mean is that we allow fluctuating geometries, just as Einstein told us we should be, but in universes that asymptotically look like anti-de Sitter space. Okay? And the basic idea is that the general structure is true in any number of dimensions. Okay, and I'll talk about some examples in lower numbers of dimensions. Great. I'm saying that this is a general structure that is it's solved to the standards of physicists, perhaps not to the standards of mathematicians, in the sense that there is a structure that we believe to be true, and we can check in any one of a number of examples, some of which I'll present to you. And so I think it's solved in the sense that we understand, I think, what quantum gravity is in de Sitter space and in anti-de Sitter space. And I already told you what it is. Turns out that gravity in anti-de Sitter space is a conformal field theory.
You're saying that in all dimensions or in some specific?
Okay. To the extent that we understand it, every theory of gravity in anti-de Sitter space is a conformal field theory. And there's no statement about dimension there. So it's true in any number of dimensions. Yeah. There's some examples that are understood much better than others. So, for example, the most famous version of this is between a 5-dimensional theory of gravity and a 4-dimensional conformal field theory, known as n equals 4 Yang-Mills, as you know. But this is a general structure that seems to be true universally. And in every case where we can actually do calculations and check it, in any number of examples, in any number of dimensions, it seems to work. Good. So what's going on here? Why is this working? Okay. So what is ADS? Anti-de Sitter space is just hyperbolic space, okay? But in Lorentzian signature rather than Euclidean signature. Okay, so it's the pseudo-Riemannian version of hyperbolic space, okay? And if you wanted, it's a geometry. And if you wanted, I could go ahead and write down the metric of anti-de Sitter space for you in your favorite coordinate system. But in the spirit of a colloquium, I'll just show you a picture. Okay, so this is a famous print by Escher. And fortunately, I don't actually need to write down the metric for you because everything that you need to know about anti-de Sitter space or about hyperbolic space is contained in this picture. Okay. So this is actually a picture of 2-dimensional hyperbolic space, the Poincare disk, or the Poincare ball in a higher number of dimensions. But basically, everything you need to know about anti-de Sitter space or hyperbolic space is in this picture. And all you need to know is that the rule for the geometry of hyperbolic space is that as you go out towards the boundary of hyperbolic space, each one of these fishes rescales in size by a constant factor. Okay. So for example, if you look at, I don't know, this orange fish, it rescales in size by a factor of 2, and then a factor of 2, and then a factor of 2, and so on and so forth, until you reach the boundary. the boundary is in one less dimension. So here, hyperbolic space was the disk, and the boundary was the circle. And because as you go to the boundary, distances rescale by a constant factor, as you go out to the boundary, the symmetries of anti-de Sitter space become conformal symmetries of the boundary. Okay? And in a theory of gravity, in ADS, the symmetries of the theory of gravity will be the isometries of hyperbolic space, the isometries of ADS. And out at the boundary, those are realized as conformal isometries or conformal transformations of the boundary. Okay? That's the relationship between gravity and ADS and conformal field theory. Good. And that's why a theory of gravity in an asymptotically anti-de Sitter space is a conformal field theory. And here I can at least partly answer John's question, because we can then go ahead and try and check this in every sort of theory that you understand. And here I've provided a list, a very partial, very, very partial list of some of the examples where this can be checked. On this side over here, I have a list of theories of gravity, okay? Some of them are simple theories of gravity, like this is general relativity in 2 space and 1 time dimensions. These are fancier versions of that. This is something known as Vasiliev gravity. This is a very fancy string theory down here. And then on the other hand, we have a list of conformal field theories, okay? And this top entry at the list is exactly that conformal field theory I presented to you earlier, okay? It was the one of interacting spins in 2 dimensions, known as the 2D Ising model. Then we have some other sorts of models that may be familiar if you studied statistical mechanics or statistical physics or something like that. And then down here, you get fancier theories. So for example, this is what's known as a Yang-Mills theory, similar in character to the kinds of theories that govern the standard model of particle physics, albeit in a sense, it's a much simpler one because it has more symmetry. And then the final thing, which is the thing that I didn't tell you, which is this column in the middle, is a dimensionless number. Okay. In the language of conformal field theory, it's essentially what's known as the central charge of the theory, but it has a very straightforward physical interpretation. And the basic idea is that hyperbolic space has a length scale, right? It's a curved manifold, so it has a length scale. And when I talk about a theory of gravity, when you talk about physics, dimensionful numbers make no sense. You should never talk about them. You should only talk about dimensionless quantities, right? And it's that length scale in units of what's known as the Planck length, okay? So you could either think about it as that length scale in units of h bar or in units of Newton's constant. But basically, it's a dimensionless constant that tells you how strong the effects of gravity are in the gravitational language, or how many degrees of freedom you have in the conformal field theory language. Okay. So for example, here, this number is relatively small, which means that we have relatively few degrees of freedom in the conformal field theory, and that it's a very quantum-y theory of gravity, in anti-de Sitter space. And down here, you have theories with many degrees of freedom, which correspond to classical theories of gravity, or what we sometimes call semi-classical or nearly classical theories of gravity on the other side. And in order to understand this, are there any questions before I continue?
Is there like how many more things can you put on this list? Like, is it
Well, there's 3 dots. There's 3 dots here, so lots. Yeah, no. There's lots and lots. I mean, this original paper by Maldacena has 30,000 citations that describe this example. Probably there's probably an average of at least 1 more example per citation. So I think there are lots of these. Some of them are continuous families, so infinite, if you like counting infinities that way. But yes, there are many, many examples. I mean, I think one of the things that I should mention as a caveat is that this relationship is what in physics parlance we call a duality. And one of the defining features of a duality is that if it's easy to study on one side, it's hard to study on the other side. That's almost the definition of what physicists mean by duality. And it's rarely so, you have to be sort of lucky to find something that you can study on one side and then match to something on the other side. Okay. In some cases, this is why physicists find dualities useful, because they translate a hard problem on one side to an easy problem on the other side. But on the other hand, if you're not entirely sure that something's correct, you have to be a little nervous, and you have to make sure to check it carefully. And so, I spend my life studying some of these easier models that live up here, because those are cases where you can really compute everything precisely on both sides and do some matches. Okay. And a lot of the sort of evidence for ADS-CFT comes from these fancy examples down here, where usually people are using the symmetries of the theory or studying symmetry-protected quantities that allow one to match systematically on both sides. Yeah, but there's many, many examples. Right? Established, maybe I would say, with varying degrees of rigor. Maybe not rigor in the mathematics sense, the physics sense. Good. Okay. But what can we learn from this? Okay, my core interest is in gravity. So to me, the most exciting question is, what could we learn about gravity in this case? Okay, so to do that, let's think about what's going on here. Okay, so I told you that we were studying gravity in anti-de Sitter space. I drew a picture of anti-de Sitter space here. Okay, this was anti-de Sitter space. It has some particular length scale. And the basic rule for thinking about gravity in anti-de Sitter space is that you should think about it like gravity in a box. And if L is what I called the size of anti-de Sitter space, it's like gravity in a box of size L. Okay? So what does gravity in a box look like? Good. So what does gravity in a box look like? Well, let's imagine that you have a box. Okay? And you start putting energy into it. Okay. The one thing I know about gravity, without even thinking very hard, is that if you take a lot of energy and you put it in a very small region and you keep dumping energy in, eventually it'll collapse into a black hole. Okay. And so what that means is that the typical high energy state of the theory is going to be a black hole. Okay. In particular, in terms of this number that I listed in the middle, as long as the energy is large compared to that number, the typical state is going to be a black hole. Okay. Now, there's a couple of bells and whistles, okay, because black holes, it turns out, in general relativity, are not quite stable due to quantum mechanical effects. So quantum mechanically, if you just have a black hole, it will emit radiation. That's what Hawking showed us. This is known as Hawking radiation. But it turns out that the rules of gravity in ADS are such that it's not just like a box, but it's like a box with reflecting boundary conditions. So if you emit a thermal particle, it will get bounced back and can be reabsorbed. So the typical high energy state is actually a black hole in equilibrium with its own Hawking radiation.
Are you still speaking of arbitrary dimension or?
That's true. That's true in arbitrary. Now, what do we know or believe about such black holes? Okay. Well, one of Hawking's, if not his most famous prediction, was for the entropy of a black hole. Hawking famously observed that black holes have a temperature, so they emit particles at a particular temperature. They also have an energy, right? So the first law of thermodynamics, dE is TdS, says if something has a temperature and it has an energy, it has an entropy, okay? And Hawking computed it for us. And the entropy is the area of the event horizon. And it turns out, and so for a very long time, for several decades, 30-ish years, this was a very confusing statement, right? Because we're used to things like the air molecules in this room having an entropy, but we're not used to things like black holes having an entropy, because nobody understood what the microscopic degrees of freedom were that made up a black hole. But now we have this beautiful picture where we have this list of quantum mechanical descriptions of gravity and ADS. Okay. And we understand that the typical high energy state in one of these conformal field theories is a black hole. So now you can just throw what you know about quantum mechanics at this and try and count the number of states in these systems at high energy. And what do you find? Well, you find exactly what Hawking predicted. Okay. And so this is a statement now that's true only for two-dimensional conformal field theories, which would correspond to three-dimensional theories of gravity. Just remember, these conformal field theories live on the boundary of n-de Sitter space. And here you can show that the number of states at high energies is the square root of the energy times a particular numerical coefficient. You translate that all back into the gravity language, you find that it's exactly this. So this, I think, is one of the main successes of this ADS-CFT duality. It has sort of allowed us to come up with a fully consistent quantum mechanical picture where you can count the states of a black hole. And just because it's a mathematical audience, I'll advertise that this counting formula of states in conformal field theories is something that mathematicians knew a version of for a century. It's basically a souped up version of a famous resultant number theory, where you count the number of partitions of an integer for large integers. Okay? And the proof of this formula involves modular invariance, and that's not an accident, okay? Because these conformal field theories also exhibit versions of this modular invariance. Okay. But now we're using this not to count partitions of an integer, but to count the quantum states of a black hole.
Are you saying that Hawking's prediction is an improved version of the formula, or does this prove this an improved version of their formula?
So it's interesting. Physicists discovered that, Hawking discovered this formula. There is a physicist named John Carty who discovered this formula. And then there was a third physicist who then observed that actually they turned out to be the same thing. And I think you should think of the conformal field theory formula as a souped up version of the Hardy-Riemann formula. Good. Thank you. Any other questions? Great. Okay. So this is a sort of generic version of the picture, but in some cases you can do this incredibly precisely. Okay. So let me give you maybe one of my favorite examples of this at work. Okay. So this was, I think, the fourth example on that list that I showed you on the other slide. Okay. This is a particular conformal field theory. So it has some states. Those states have energies. Okay. And so you can enumerate the states and count them and calculate their energies and so on and so forth. And let me just list a few of them for you, just so you can get an idea of what's going on. Okay. So there's one state with no energy. In the CFT language, we call that the identity operator. Right? It does nothing. In the gravity language, that's just empty space. Then it has one state with energy 2 in some units. And what is that? That's a lonely graviton bouncing around in this box. And then it has 197,883 other states with energy 2. And 21 million, so on and so forth, states with energy 3, and so on and so forth. Okay.
So where does the monster come?
I'll tell you what a monster is. Okay. But first, let me tell you where black holes come. Okay. Because these 196,883 states are dual to a black hole. You could go ahead and look at Hawking's formula for the entropy of a black hole. It says that the entropy is the area in Planck units. So I told you the energy. That means I know the mass of the black hole. So I can go open your favorite book on general relativity and compute the geometry of that black hole. You can compute the horizon area, you divide by L Planck, and you get 4 pi. And indeed, you take the log of 196,883, and it's 4 pi within about 2%. But then you remember that this was actually not classical general relativity. It was, where was it on this list? It was this example here. So 24 is big, but it's not infinity. Okay. So it is a not quite classical theory, which means you need to compute quantum corrections. Hawking's calculation of the Bekenstein-Hawking entropy involved a classical general relativity calculation. But you can always study quantum corrections too. So for example, you can use Feynman diagrams to compute quantum corrections to the Hawking entropy. Okay, and if you do it in this case, you find that actually the entropy is not 4 pi, but it's 4 pi minus 1/2 log 2. Okay, so you put a factor of 1 over the square root of 2 out here, and then suddenly this agrees not to within 2%, but within about 0.2%. Okay. And actually, there's an infinite series of subleading corrections, which you can compute, and you can actually reorganize them into a convergence series for this integer. Okay. That's a little subtle. Strictly speaking, it's an asymptotic series, but there's a trick from number theory by Rademacher, who taught us how to reorganize it into a convergence series for that number. And also, you can also make mathematics predictions based on this. For example, remember when I described a spin 1/2 particle as holomorphic sections of a line bundle on P1? Okay. That's because you were considering a particle that was moving on a sphere with whose phase space was a sphere. Here, we're studying a theory of gravity, and so the corresponding phase space is the moduli space of Riemann surfaces. And this counting of the number of states is the counting of holomorphic sections of a particular line bundle over the moduli space of Riemann surfaces. And so you can actually turn this black hole entropy into a prediction for the number of holomorphic sections over a certain line bundle on the moduli space of Riemann surfaces. Okay, that's and that's quantum mechanics. That's what quantum mechanics is. Physicists won't tell you this, but what they're secretly doing all day is counting holomorphic sections of line bundles. Right. And here you can actually, it's a particular line bundle for those who are really into moduli of surfaces. It's the number of holomorphic sections of particular line bundle on, I suppose. This is a conjecture, by the way. This is not proven. There's some subtleties there. That equal should be in quotes. Yes.
Does the moduli space of curves arise because of the conformal field theory, or not?
This is something that we learned from conformal field theory. This is what you get by doing a straightforward quantization of general relativity. Okay, there's some bells and whistles. It's not actually general relativity. It's a much simpler version of general relativity related to, it's what we would call chiral theory. It's related to where those chiral and meromorphic conformal field theories. And this is one way of saying what the gravitational prediction is for the number of states. Okay. I should mention there's some subtleties here, which is, first of all, these things are very hard to compute. They're very hard to compute at high genus. But actually, if you try and do a dumb approach to this, and you just use some semi-classical methods, you actually find that you can show that it's a divergence series. So it needs to be regulated in some way. And so this equal should be equal in the sense of some zeta function regularization or something like that. Actually, this is, yeah. So there's this equal should be in quotes, but I think there's some precise version that we could talk about in more detail.
Oh, yeah, that's dimension of H0?
Yeah, yeah. Good. Any other questions? Great. Okay.
I think for this, you didn't say anything but monster, but
Oh yes,
I was a great
yeah,
friend of John.
yeah.
One dream.
Yeah.
And the dream was that monstrous Grunstein could be explained by having some natural action of the monster on the cohomology space of a manifold of dimension 24.
I talked to him about this, and I could never. I would love that. It would be amazing if there was an explicit relationship that I could articulate here, but I'm not aware of one. Just for those who don't know, 196,883 is also the dimension of the smallest irreducible representation of the monster group. And indeed, the conformal field theory that I'm describing here was the first example of an object that was discovered whose symmetries were that of the monster group, which is one of the dimensions of these representations of here. And so if there was some, what's that?
The 214 is also news.
Yeah, it's the next graph. Yeah, and so I would, yes, I thank you for that comment. Very, very much appreciated.
Yes, there like a similar interpretation of the number 2 million.
Yeah.
Like in terms of sum or some. Intentional.
So this 2 is that 2.
Ah, I see.
Okay. And so you just replace that with 3. Perfect. Great. Thank you. Good question. Yeah.
If these dimensions are integers, how high do you go?
Okay. There's a subtlety, right? There's lots of subtleties here. So first of all, this moduli space is not a manifold. It's stacked. Right? A word I learned from mathematicians, unfortunately. So physicists would call it an overfold. Mathematicians would call it a stack, which means that these numbers are actually rational numbers, not integers. Okay. Okay. Well, that's one way of addressing the question. Interestingly enough, so after I wrote this paper, there was a follow-up paper where it was observed that all of these can be counted using what's known as topological recursion. You know, a crude approximation to these numbers is to just compute the volume of moduli space with respect to this cohomology class to the top power. That's what Mirzakhani did. Or rather, what Mirzakhani did is write down the recursion relations that would allow us to compute those volumes. That's just an approximation to the actual answer that we're writing here. But those volumes can be computed using what's known as topological recursion, which is the observation essentially that the recursion relations that Mirzakhani wrote down to compute these things are the same recursion relations that apply when you take a matrix integral and integrate it by parts, roughly speaking. And so it was later understood in 2022 that actually these numbers themselves are also computed using topological recursion of what are known as the quantum volumes of moduli spaces. So I think this is still an area. This is an area of very active research. I can't give a definite statement, but I think either this statement or some appropriate understanding of it should be true. Great. Okay. But okay, so this is all well and good. We've been able to say some precise things, but I didn't yet answer the original question that I proposed at the very beginning. So how is space-time related to entanglement? Okay. And it turns out that this ADS-CFT picture also allows us to answer that. Because it turns out that black hole entropy that I wrote down is an entanglement entropy. Remember what I started with at the beginning of this talk, is that you have these 2 entangled qubits, 2 entangled spins. They have an entanglement entropy that was 1 bit of information, 1, 2. And it turns out that all of these entropies are also entanglement entropies in a way that is very easy to see using this ADS-CFT correspondence. And in order to see that, what you need to do is draw a picture of a black hole. Okay. And here I've drawn a picture of a black hole. Okay. It's a strange sort of picture. It's a picture of what we call the causal structure of a black hole, or the Penrose diagram of a black hole. What does that mean? So it's a picture where time runs vertically and space runs horizontally, and light rays travel on 45-degree lines. And in terms of the picture of hyperbolic space that I wrote down over here, where was it? Okay. I'm ignoring the angular direction, and I was only plotting the radial direction. Okay. So, for example, if you were to study just anti-de Sitter space, so for example, there's a circle at every point on this diagram. And out here is the boundary where the conformal field theory lives. So here there's a circle that's becoming very, very large. And what a black hole looks like is that circle shrinks to some finite size. The place where it achieves its minimum is what we call the event horizon of the black hole. And then it expands again to have an infinite size over here. So actually what this is teaching you is that the quantum mechanical description of one of these black holes is in terms of a pair of conformal field theories. Because I have 2 boundaries that here. I call this a red boundary and I called it a green boundary. And actually, this geometry that connects them is something that we call, in fanciful terms, you call it a worm, okay, or an Einstein-Rosen bridge. And right, so this summarizes that statement. So the geometry connects a red boundary to a green boundary. And then you can ask, what is the quantum state describing this black hole? Well, it's the same, it's exactly the state that I wrote down for you on the second slide of this talk. Okay. It's an entangled state, not between a red spin and a green spin, right? That was the first thing I showed you. But a CFT is just a collection of spins. Okay. So it's an entangled state between a red collection of spins and a green collection of spins, or a red conformal field theory and a green conformal field theory. And the point is that from the point of view of an outside observer, okay, it appears that you're in any number of states according to the Boltzmann distribution, and the entanglement entropy is the entropy of this black hole. So what are we learning? What we're learning is that this wormhole that connects distant parts of space-time actually has its origin in the entanglement of two quantum mechanical systems.
So what you have is the intersection of, if you really want an intersection in a surface system.
Which show
The event horizon. No, yeah.
This is a circle. Because remember, I was ignoring the angular direction. So there's a circle at every point in the
Especially back to 2 dimensions, I think in 4 dimensions.
which would be a sphere. Okay, the same diagram is true in higher dimensions, so then there would be a 2-sphere at each point. And that 2-sphere shrinks to 0, has a finite size here. We call that size, so we call that 2-sphere the event horizon, and we call that size the area of the event horizon. Yeah. So this is a perfectly smooth, nice place. Yeah. This is not, this is the singularity center. Okay.
Right. So all is clear except for the word is.
Wait, I didn't use this. A black hole is? Oh, that is?
No, that's one of is.
Good, okay. So maybe the next slide, yeah, okay, well, no. Okay. This is an entangled state between quantum systems. This is a geometry that connects two distant points in space-time. So what you're learning is that you could take two collections of spins that are distantly separated. And if you paid an experimentalist a lot of money, okay, they could entangle these two systems in this exquisitely prepared quantum state. And then from the point of view of one of the systems, that would be indistinguishable from there being a black hole sitting right there. Okay. And the other, could be on the other, could be an Alpha Centauri or whatever. The other one, could be very far away, but like if you jumped into the horizon of that black hole, it's a little more complicated because the causal structure is more complicated. But the other end of that black hole is this place in Alpha Centauri. And I say that in slightly more outrageous terms on this. Okay. Because you could also go on the other, this is what I was saying, right? You could start with a collection of green spins and a collection of red spins, entangle them with exquisite precision, and the result would be indistinguishable from a black hole where the two regions are connected by a wormhole. And then you can make even more outrageous statements if you want. Okay. So this, I think, is all, I don't want to say old work, but this is, in the last decade or so, things that we've understood. Maybe in the last few minutes, I can talk about some of the modern work that's going on currently on trying to understand these systems. So, if you look at the example that I gave you earlier with 196,883 and those other impressive looking integers, the reason I could compute those integers is that I was studying a theory with an extraordinary amount of symmetry. It's what we call an integrable theory. Literally in conformal field theory land, we call it an integrable conformal field theory or rational conformal field theory. But a generic system is not expected to be integrable. A generic system is chaotic. And indeed, if you ask people what the actual conformal field theory description of semi-classical general relativity, Einstein gravity, is, then you actually expect it not to be an integrable theory, but rather a disordered theory. In mathematics, people are very used to studying disordered theories using random matrix theory. In physics departments, people in condensed matter physics who study spin glasses and stuff like that are very used to studying disordered theory. And the basic idea and the basic sort of direction that I think people are moving in is the idea that gravity is actually a disordered system with random couplings, okay? And then that means that you need to choose a probability distribution over the space of couplings, okay? And as an obnoxious Bayesian, I think there's only one correct probability distribution, which is the maximum entropy probability distribution, subject to some constraints. And so I think that the consensus, maybe, I don't know if it's a consensus, the consensus of the people giving this talk is that gravity, general relativity, is the maximum entropy probability distribution over the space of solutions of the conformal bootstrap. That's what semi-classical general relativity is. And we've actually been able to study this and check this in some very precise sense. Okay. And so maybe just in the last minute or two that I have, rather than talking about semi-classical general relativity, I'll talk about a case that's not quite as chaotic, but it's sort of halfway between being integrable and chaotic, right? It's like being a little bit pregnant, you know, it's like, it's sort of one of these weird things that's like not integrable, but right on the cusp of being integrable, where you can solve this problem exactly. Okay. So there's one example that I know of where you could really solve exactly a space of conformal field theories that genuinely has disorder. And so I'll just advertise that maybe in the last minute or two of my talk. So it turns out there are examples of conformal field theories where you can actually solve the conformal bootstrap explicitly. So there's some very simple examples that are integrable theories. And this is a class of theories that just lie on the boundary between being integrable and chaotic. And it turns out there's a finite dimensional space of solutions of these theories. Okay. The solutions are labeled by even self-dual lattices of some indefinite signature. Okay. So here, C is a pair of integers. C is the same C that I told you earlier. C is an integer, so there are lattices of signature CC. And then you can solve the conformal bootstrap. Okay. You can study the observables of the theory. Okay. In this case, the observable is some sort of theta function associated to that lattice. And then you can actually define a probability distribution over the space of those lattices. Turns out there's essentially one natural probability distribution. So this is like a disordered family of conformal field theories, a disordered quantum mechanical system. We have random couplings. We've chosen a probability distribution on the space of couplings. We've computed an observable. And it turns out that the computation was actually done by number theorists many years ago, Siegel and Weil. And it turns out that what you get is a theory of quantum gravity. So for example, if you compute the partition function, interesting, there's a talk on CFT partition functions on Riemann surfaces, you know, just at 2 o'clock earlier today. But if you compute the average partition function of such a theory surface, you get a sum over ways of filling in that surface with three-manifolds. And that's what quantum gravity is. It's a sum over geometries. Right? Einstein taught us that gravity is a theory of fluctuating geometries. So therefore, in quantum gravity, you should sum over all possible geometries. And in this case, this is an explicit example of a disordered conformal field theory that is a sum over geometries. And in particular, it's a sum over a class of geometries where we can, you know, enumerate all of the possible geometries and compute all of the quantum corrections in order to show that this sum works. Good. And where is all of this going? This is all going towards, let me say, a generalization of random matrix theory to more general systems, not just to random matrices, really what I would call random field theories, random confolding. The conjecture is that general relativity is a probability distribution over the space of conformal field theories. Semi-classical general relativity is a probability distribution over the space of conformal field theories. And what Einstein taught us about general relativity is that, you know, the action of a space-time in general relativity, the Einstein-Hilbert action, is computing the statistical distribution of certain conformal field theory data. Okay. And that formula involving the Hardy-Ramanujan formula and black hole entropy is one example of that. But we found many other examples where the Einstein-Hilbert action of an appropriate geometry is the statistical distribution of conformal field theory data. Okay. So I'm just about out of time, so I think I'll end there. There's an important slide that you can ask me about how to interpret this, but unless someone asks, I won't tell you about it. And just maybe leave you with some thoughts for the future. So I think there's many interesting directions to go. Understanding the structure of disordered quantum theories, understanding how to think about quantum mechanics and quantum field theories as information theoretic objects, solvable example of black holes, cosmologies, and so forth. Attacking this, you know, what do I call it? The genome project of theoretical physics for the Apollo program. Every time I give a talk, I choose a different analogy for whether conformal bootstrap is the Manhattan Project, the Apollo program, or the genome project of theoretical physics. Whichever it is, we should solve it. So these, I think, are some of the open problems. And I think that, you know, given that this is a mathematical audience, I think it's important to understand the kinds of mathematics that might go into trying to solve these problems in the future. I'll stop there. Thanks.
Are there any questions for the speaker? Or are there any other questions for the speaker?
All this is somehow putting in the sort of PDF, the philosophy, that's usually how it works. Yeah. There are other kinds of dualities that don't involve that picture, right? Electromagnetic duality is the prototypical one where, you know, there's no filling in of anything, you know. This particular family where you're studying theories of dynamical geometry, and that geometry has to emerge from somewhere. Yeah. And the way it emerges here is that you sort of have a boundary, you fill that, and you sum over all the ways of filling. But, you know, I mean, that's not, you know, that may just be a very particular feature of the way gravity and de Sitter space. Gravity, like we don't live in, like this space-time we live in is not anti-de Sitter space, not hyperbolic space. We have that sort of understanding. Might be that the actual theory of quantum gravity in space we live in, nothing to do with that.
Other questions? Yes.
Quantum gravity is so much. I did let's see if you understand that it's really just magnetic fund and whatever something's.
Well, I mean, okay. I mean, from the field theory point of view, gravity is not renormalized. Which means that quantum field theory works very well as an effective theory with cutoff. But when you try and go to very high energies, like Planckian energies, quantum field theory, you know, general relativity as a quantum field theory fails to be predictive. So that's just a feature of general relativity as opposed to Yang's theory. But I don't know, maybe you're looking for some other sophisticated answer. It's so much more complicated. It's all well divided. We're trying to do that. Yeah. I mean, we're trying to, like, you know, I mean, yeah, I mean, we're trying to. Follow up question. So you have some version on relativity. What experiment would one do? Usually the question I get in what experiment? I mean, if you ask me, what the most exciting experiments are to probe quantum gravity. They don't involve anti-de Sitter space in particular, because we always do an anti-de Sitter space. Many of the most exciting experiments involve cosmology. You know, our universe is expanding, which means that at very early times it was very, very small, and very, very dense. Okay, which means that quantum gravity would be necessary in order to understand the very, very early universe. So many sorts of experiments that people talk about that could be interesting are cosmology observations that would tell us about the structure of the very early universe. That's a very difficult experiment because you know, the universe became opaque to light when it was sufficiently, you know, once it became a plasma with charged particles operating freely. So it's very hard to observe an arbitrary flying to the past, but still you might see some imprints there. You know, I mean, there are tests of Lorentz invariants, for example, that probe time scale physics. And so there are experiments you could do, but it's not easy. That's, yeah.
Well, okay, we'll take one more question. Done?
You said about making fast. So I don't know, I mean, there's a hundred different colors. The first example is but you showed with but is there a way to actually get the J's in and the coefficients in the J series of the holomorphic indices? Okay, I don't know. No, they don't.
Oh, the J function. Sorry. Yeah. I mean, if the conjecture is right, then yeah. Because there was it was shown by Lorenz Everhard in Amsterdam how to get the, you know, how to get, so as you know, Mizukami and followed by Inard and Renton showed how moduli space volumes can be gotten using topological recursion. There was later work by Everhard and friends showing how you can get these more refined counting problems, so-called quantum volumes using topological recursion. And then I suppose I just made a conjecture which says that you can get the J function out of that, right? You just replace 2 by delta, and some of the delta, and you get the J invariant. So yeah, I guess so.
And do all the numbers, I mean, if those numbers that you mentioned, that continues to all of the coefficients of the J function?
Yeah.
And it corresponds to higher and higher energy.
The partition function is the J function. Okay, I didn't write that down because, you know, that's for people, I don't know, that seemed too specialized, but yeah, so the partition function of the J invariant.
Okay, great. I think we'll end it here.